AI agents like AWS DevOps agents or Kiro are designed to write, test, and refine code entirely on their own. But in practice, that rapid execution often comes to a grinding halt. When these tools fail in an enterprise environment, engineers typically blame the large language model. They assume it hit a context limit or hallucinated a bad path. The reality is an infrastructure problem. The traditional cloud architecture is suffocating the agent with slow feedback loops. Standard deployment pipelines are built for human cadence. A developer commits code, waits for a build step, provisions resources, runs tests, and deploys. On top, a standard 15-minute pipeline resolves a single human-driven change. Below, an AI agent requires dozens of rapid micro-iterations in that same timeframe. Waiting minutes for a deployment loses context. This friction acts as a choke point, destroying the agent's ability to course correct. Implementing autonomous code generation requires abandoning slow, cloud-dependent testing cycles. The architecture must be explicitly redesigned to provide sub-second feedback. An AI agent operates through a strict operational cycle. It reads an instruction, evaluates the context, prints code, and tests the result. This read, eval, print loop, or REPL, dictates its velocity. To maintain velocity, developers must implement a strict architectural mandate: default to local emulation before touching any cloud resources. The AWS Serverless Application Model, or SAM, makes this practical. It allows an agent to invoke Lambda functions locally, bypassing the lengthy cloud deployment phase entirely. This schematic shows a strictly bounded local host environment. Lambda and API Gateway sit entirely isolated from broader cloud dependencies. By bringing DynamoDB local into that boundary, the agent can test operations instantly. Network latency is removed.
This localized testing paradigm is not limited to simple request-response APIs. Distributed data and analytics workloads require the same isolation. An agent can isolate AWS Glue logic and validate transformations against sample datasets using Docker. It inspects intermediate results locally, only moving to managed services for scale testing. Local emulation shrinks the agent's feedback loop from minutes to seconds. This speed is the foundational prerequisite for autonomous code execution. Emulation has limits. Eventually, an agent must interact with managed cloud resources, like simple queue service or simple notification service, which cannot be perfectly replicated locally. To cross this gap, the system relies on hybrid testing, utilizing infrastructure as code. Agents use tools like the AWS Cloud Development Kit or CloudFormation to deploy small, isolated preview environments on demand. A lightweight connection extends from localhost out to a small, isolated cloud stack dedicated to hybrid testing. The stack spins up, the agent runs smoke tests, returns a validation signal, and immediately tears everything down. This workflow treats the cloud as a strict, predictable test dependency rather than an open sandbox for experimentation. Hybrid testing grants the agent the reality of live cloud execution while maintaining tight control over operational scope and testing latency. Fast system feedback guarantees nothing if the agent cannot understand where to make changes in the codebase. Standard repositories rely on implicit tribal knowledge. Rules about where specific logic belongs are rarely documented in a format an AI agent can perceive. The solution requires implementing strict domain-driven design. Code must be organized so that an agent can safely modify business rules in the domain layer without breaking the external infrastructure layer. This diagram demonstrates hexagonal architecture. It protects the core business logic in the center and attaches external AWS dependencies purely as outer adapters. Operating within this structure, the agent can safely iterate on the central logic. The outer adapters remain locked and unaffected. Human intuition must be explicitly encoded into the project. Tools like Kiro use machine-readable governance, such as steering configurations or agent.md files, to define architectural constraints. Layered testing strategies, utilizing unit tests and contract tests and smoke tests, act as an executable specification. When a test fails, it provides objective validation. The agent reads the failure, infers the exact expected behavior, and corrects its code. Explicit boundaries and steering files translate human architectural intent into a deterministic map that an AI can navigate safely. Local emulation loops and explicitly designed codebases combine to feed a highly optimized continuous integration pipeline. Frontier agents utilize this setup to navigate and resolve complex cloud incidents autonomously. This agent-native architecture integrates local emulation, domain logic, and CI/CD guardrails. Inside the emulation block, the agent iterates rapidly, executing hundreds of validations per minute. Once validated, the system allows a single verified push outward, passing through guardrails into production. Governance remains central to the pipeline. Automated reviews and branch protections keep human engineers in the loop for high-impact decisions. Trusted production-level AI autonomy relies on deliberate architectural guardrails as much as raw model reasoning. This software-level autonomy requires massive, specialized physical infrastructure to run the foundational models. The speed and reliability that agentic AI demands rely entirely on vertically integrated data centers, utilizing custom silicon and extensive cooling systems. Modern cloud engineering requires adapting to two distinct structural changes. First, you must accelerate the feedback loop by leveraging localized system emulation. Second, you must eliminate structural ambiguity by enforcing deterministic, machine-readable codebase boundaries. When architecture aligns with agentic workflows, AI agents act as capable extensions of the engineering team, handling iterative development autonomously. The future of cloud engineering requires designing architectures that your AI counterparts can actually build within.